Tutorial sheet 3, question 7. An FM transmitter is modulated with a single sine wave. The output for no modulation is 100 watts into a 50 ohm resistor. So that 100 watts is going into a 50 ohm resistor. The peak frequency deviation of the transmitter is carefully increased from 0 until the first sideband amplitude in the output is 0. Under these conditions, determine the various output powers that we've been asked to do. So first of all, it says we have no modulation, and we have purely that we have 100 watts going into 50 ohms at that point. So there's no frequency modulation at this stage. Then the peak frequency deviation, delta F, is increased until the first sideband amplitude, which is determined by the Bessel function J1 of beta, is equal to 0. So if I think about that as a frequency spectrum, I'm going to have Fc here, and then let's expand this quite out so it looks quite large. So we're going to have Fc plus Fm and Fc minus Fm. So we're going to initially have a carrier component, and then we're going to increase delta F so that this will appear and then increase, and then it will decrease again until it goes back down to 0. So we've got to find out the value for when J1 of beta is equal to 0 so that we can get the modulation index. If we do this, and again I'm looking at the tables in the notes, I'll just show those so that you know which part of the notes that I was using. So it's the Bessel function table. What I'm looking for here is that when J1 of beta goes to 0. And J1 of beta goes to 0 when beta is roughly equal to 3.8. So that's the first useful bit of information. So we've got an estimate for what our modulation index is. The first thing we have to calculate, A, is the average power at the carrier frequency. So the total power in our system, which is 100 watts, is 100 watts, which is also equal to Vc squared over 2 times 50. So that's the total power. So we can work out Vc, and if we rearrange that equation, we get Vc is equal to 100 volts. So the carrier power is equal to Vc squared over 2R times J naught of beta all squared. J naught gives us the amplitude of our carrier component, which is equal to 100. And if we work out J naught, and if we look up in the table, J naught of beta is roughly equal to minus 0.4. Obviously we're going to square that. So that's equal to 16 watts approximately. Part B asks us the average power in all the remaining sidebands. Well, this is simple because we know the total power, which never changes, that's 100 watts. We've calculated the power in the carrier. So the difference between these two is what's left in all the other sidebands. So simply the power in the sidebands equal to 100 minus 16 is equal to 84 watts. Then we need to work out the average power in the second order sidebands. So that's both sidebands. So in this case what we've got is Vc squared over 2R times J2 beta squared, and then we have to multiply that by 2 because we've got 2 sidebands. So this first equation works out the amount of power in one sideband, and we double it for the 2 sidebands. And that, if we work that out using the table, BC squared over 2R, and then we have, again, it's 0.4 approximately, and that gives us 32 watts.